speaker is going to be Debajyoti Kar, and this is a paper with Arindam Khan and Andreas Wiese, and he will tell us about approximation schemes and structural barriers for the two-dimensional knapsack with rotations. So, Debajyoti, the floor is yours.
Okay. Hi. Thanks for coming to the talk. And this is the joint work with Arindam Khan and Andreas Wiese. Okay. So imagine you are packing your bags for stock and you have made a list of items that you want to carry along with you. So for example, you have clothes, shoes, water bottles, electronic equipments, etc. But now your airline comes up with this strict policy of allowing just a single suitcase per person. So then what do? Unfortunately, now you do not have enough space to accommodate all these items in one suitcase. So then naturally, you would want to pack as many items as possible into the suitcase. And as you can see here, that most of the items are sort of rectangular in shape. So computationally, this is what is called the two-dimensional geometric knapsack. So to abstract things out, formally, we are given a knapsack which is represented by a square which has a side length of k, and assume that k is an integer. And you are given a collection of axis parallel rectangles where each rectangle is specified by its width and its height, which are both integers between 1 and k. And now your goal is to pack the maximum possible number of rectangles into the square in such a way that no two of the rectangles overlap each other. And throughout this talk, I'm going to assume that the rectangles can be rotated by 90 degrees. That is, for every rectangle, there are two possible orientations in which you can pack the rectangle. So for example, consider the orange rectangle. Either you can place it vertically in this fashion, or you are allowed to rotate it by 90 degrees and pack it in this fashion. And under this constraint, your goal is to place the maximum number of rectangles into the square. So for example, for this instance here, we have a packing that packs 6 of the input rectangles. So as you can imagine, this problem has wide applications in practice, ranging from loading items onto trucks to applications in robotics, VLSI design, then placing maximum number of advertisements on a billboard, cutting stock problems, etc. So what's known in theory? So it turns out that the problem is strongly NP-hard even for the special case when all the input rectangles are squares. And therefore, we look for approximation algorithms. So an alpha approximation is an algorithm that packs at least a 1 by alpha fraction of the optimal number of rectangles for every input instance. Okay, so let's look at the previously known approximation ratios for the problem. So back in 2004, Janssen and Zhang gave a 2 plus epsilon approximation. Subsequently, in 2017, this was improved to a 4/3 plus epsilon approximation. And prior to our work, this was the best known approximation ratio for the problem in polynomial time. But it also turns out that if you allow higher running times, or if you make certain additional assumptions about the input, then better approximation ratios are possible. So for example, there is a QPITAS known for the problem, assuming that the side length of the square is quasi-polynomially bounded in the number of input rectangles. And then there is a 5/4 plus epsilon approximation known in pseudo-polynomial time. That is, if you assume that the side length of the square is polynomially bounded in the number of input rectangles, then the 4/3 approximation improves to 5/4. And finally, for the special case, when all the input rectangles are squares, there is a PITAS known. So this is more or less a complete description of the approximation ratios known for the problem. So after all this, the big open question that remains is, does there exist a PITAS for the general problem? That is, now we do not want to make any assumptions about the input. We do not allow for super polynomial running times. Can we get a 1 plus epsilon approximation in general? And in fact, there was a survey in 2017 by Christensen, Khan, Pokuta, and Tetali, where they made a list of the top 10 open problems in geometric packing, and obtaining a PITAS for the rectangle packing question was listed as one of these 10 problems. And the main result of our work is that there indeed is a PITAS. Okay, So now I'll try to briefly give an overview of our techniques. So the high level idea consists of two basic steps. So first, we need to show the existence of some kind of structured packings. That is, intuitively, we'll show that starting with the optimal packing of the rectangles in the square, we can rearrange the rectangles present in the optimal packing in order to obtain an alternate packing that has some additional structure. And the hope is that the best such structured packing can be computed efficiently using some dynamic programming framework. Okay, so what are these structured packings? So a structured packing is essentially a packing that satisfies certain additional constraints. So pictorially, we have the space of all possible packings, and the optimal packing lies somewhere here. And then, as a subset of this, we have the space of all possible structured packings, and the optimal structured packing sits somewhere here. And the constraints that we want to impose should be such that the best structured packing, that is the optimal structured packing, should be easy to compute. That is, we should be able to compute this optimal structured packing in polynomial time. And further, we also want that the number of rectangles present in the optimal structured packing should be at least a 1 minus epsilon fraction of the optimal number of rectangles. That is, in other words, starting with the optimal packing, we want to show that by discarding only an epsilon fraction of rectangles, we can get to a structured packing. And these two things together will give us a PITAS. Okay, so then what kind of constraints should we look for? Or what kind of structured packings do we want to restrict ourselves to? So for this, let us start with the optimal packing of rectangles inside the knapsack. And our goal is to restructure this packing in order to obtain a structured packing, possibly by discarding an epsilon fraction of rectangles. So in order to do that, first let us start by classifying the rectangles present in the optimal packing. So we call a rectangle to be large if both of its dimensions exceed delta k, where delta is just some constant depending on epsilon. Then a rectangle is said to be small if both of its dimensions are at most delta k. And among the remaining rectangles, if the width of a rectangle exceeds delta k, we call it horizontal. And if its height exceeds delta k, we call it vertical. So let's look at these classes of rectangles one by one. So first, consider the large rectangles. So it is easy to see by an area argument that since the area of each large rectangle is at least a delta square fraction of the area of the knapsack, so therefore in any feasible packing, the number of such large rectangles is only going to be at most 1 by delta square. And therefore, we can do the following. If the total number of rectangles present in the optimal packing is only at most, say, 1 by epsilon delta square, which is just a constant, then we can essentially compute the optimal packing by a brute force enumeration. Otherwise, we know that the number of large rectangles is only going to be an epsilon fraction of the optimal number of rectangles. And in that case, we can afford to discard all the large rectangles. Okay, so next consider the small rectangles in the optimal packing. So although in principle, there can be an arbitrarily large number of such small rectangles, but you can think of these small rectangles as being like sand particles sprinkled in the packing. And indeed, it turns out that there are some standard greedy algorithms by which we can repack these small items, these small rectangles at the end. So for the time being, assume that these small rectangles can also be neglected. And now we are left with the packing of the horizontal and vertical rectangles. And indeed, it turns out that the core of the hardness of these rectangle packing questions lies in packing these skewed items. And the reason behind that is that these horizontal and vertical rectangles can be packed very tightly. They can tightly fit into each other. And this boundary curve between these rectangles can have an arbitrarily large complexity. Okay, so then a natural structural property that we can look to impose is to look at packings where these interactions are completely absent. And this is what motivates what are called container packings. So formally, a container packing is a packing which consists of a constant number of horizontal and vertical containers. So a horizontal container is a rectangular region inside which a set of horizontal rectangles are stacked one above the other, and analogously inside a vertical container, a subset of vertical items are stacked one beside the other. And the whole knapsack is partitioned into a constant number of horizontal and vertical containers. And as you can see, the advantage of doing that is now these interactions between the horizontal and vertical rectangles are now completely absent in these kind of packings. And the most natural way to think of these packings is to think of a bookshelf that is partitioned into these compartments, where inside each compartment, the books are either stacked one beside the other or one above the other. So this is what represents container packings. So once we have fixed the structured packings we want to look at, the next question to ask ourselves is, can we actually compute the best container packing? And indeed, it turns out that yes, there is a p-task to compute the best container packing that uses only a constant number of containers. And by best, I mean the container packing that packs the maximum number of rectangles. And this can be done via a reduction to the generalized assignment problem, but let's not go into that. So once we have this, now our task reduces to a completely structural question. That is, how many rectangles are present in the best container packing? That is, formally, if we let opt container denote the best container packing, that is the one that packs the maximum number of rectangles, then of course this is going to be a lower bound on opt. And the question that we are interested in is, what is the smallest value of alpha such that the optimal container packing packs at least a 1 by alpha fraction of the optimal number of rectangles. And because there is a p-task to compute the best container packing, this alpha is going to be the approximation ratio of our algorithm. And indeed, it turns out that previous works have tried to establish upper bounds on this alpha. So for example, the initial paper of Janssen and Zhang showed an upper bound of 2 plus epsilon on alpha, and the subsequent Fox paper in 2017 improved this to 4/3 plus epsilon. And in our work, we finally show that this alpha is in fact at most 1 plus epsilon. And this is how we get a p-task. Okay, so now I'll just give a very high-level overview of how we managed to show this improved upper bound on alpha. So again, we start with the optimal packing of the horizontal and vertical rectangles. And to this packing, we apply what is called the corridor decomposition framework, which intuitively states that it is possible to partition the knapsack into a constant number of rectilinear polygons such that each rectangle completely lies inside one of the polygons. And then what prior works have done is to apply some kind of a corridor processing scheme to these corridors. So this intuitively states that by discarding some rectangles from the corridors, the remaining rectangles can be repacked into a constant number of containers. And further, the rectangles which are discarded from the corridors, they can all be packed into a strip of width which is at most an epsilon fraction of the width of the knapsack. So all this was known before. So then from here, it is obvious to get a 2 approximation, because we can either consider this container packing which we obtain via corridor processing, or we can just consider a container packing which just consists of a single vertical container, which just consists of the orange rectangles there. So in order to get a p-task, what we essentially need is a way to repack these thin items back into the knapsack. And in order to do that, the main technical contribution of our work is a new corridor processing scheme which drastically reduces the number of containers. So in prior works, the number of containers used to be some polynomial in 1 by epsilon. So we have an exponential improvement now to polylog 1 by epsilon. But how does this help us? How does reducing the number of containers help us? So intuitively, since now the number of containers is very small, intuitively we expect that most of the containers must be sufficiently thick. That is, most of the horizontal containers must have sufficiently large height, and similarly, most of the vertical containers will have sufficiently large width. And once we have that, we kind of discard all rectangles that intersect a random strip of thickness epsilon k inside each of the thick containers. And in the process, we can show that we still retain, in expectation, we still retain an 1 minus epsilon fraction of the number of rectangles. And whatever packing remains, we push the rectangles in the remaining packing as much as possible to the left and to the bottom. That is, imagine we apply gravity to this packing to the left and bottom. And in the process, we can show that this is always going to create an empty strip of sufficiently large thickness, either at the top boundary of the knapsack or at the right boundary of the knapsack. And that is going to be sufficient to repack the thin items. Okay, so this is a very high level description of how we manage to repack the thin items back into the knapsack, but indeed this gives us a PTAS. Okay, so we also consider the weighted case of the problem, but I'll not go into the details. So we obtain improved approximation ratios for the weighted case as well when the rectangles have weights, but I'll skip this in the interest of time. Okay, so summarizing, our main contribution is a PTAS for packing the maximum number of rectangles into a square. And structurally, we now have a complete understanding of the power of container packings, both for the unweighted and the weighted case. And we also show that assuming the K-sum conjecture, any 1 plus epsilon approximation will take at least n to the power omega 1 by epsilon time. So there is probably not much hope of getting a fast PTAS for the problem. And some open problems. The immediate open question is, can we get a PTAS for the weighted case of the problem? So the approximation ratio that we achieve in our work is like slightly better than 1.5. So there is still a lot of room for improvement. And the problem is also interesting in the setting without rotation. That is, what if we allow only translations of the rectangles? So for this setting, currently the best approximation ratio is roughly 1.72. So there is still a lot of room for improvement here. Okay, so thank you.
Thank you. We have time for one or two questions. Yes?
Yeah, thanks for the nice talk. So from chip design, they are usually also like very simple shapes. So most of them are rectangles, but I think also what occurs there are like L shapes.
Yes.
Do you think that your approach also generalizes to this or to like easy shapes somehow?
To L-shaped knapsacks, you mean?
Yeah, exactly. So that you also like have.
Not exactly. So under the assumption that the rectangles
Oh,
are
not L-shaped knapsacks, sorry, L-shaped items that you.
Oh, no. No. Our techniques are very specific to rectangles. It doesn't work for L shapes, no.
Ah, okay, I see. Thanks.
Okay, just very quick.
What if there's no rotation?
Sorry?
What if there's no 90-degree rotation?
If we do not allow rotation, sir.
Yeah, yes.
Okay, so yeah, so our techniques are specific for the case when we allow rotations. So yeah, we need, so without rotations, many of the things fail. So for example, these repacking items back into the knapsack, it heavily uses that the items can be rotated by 90 degrees. Otherwise we'll have like some horizontal thin items, we'll have vertical thin items, and then, I mean, it's not always possible to repack all of them. It's not clear whether, yeah.
Is there any result on the no rotation case?
Sorry, any?
And yeah, any kind of a result, non-trivial result on the no rotation case?
Anything which is known for the non-rotation case?
Yes.
Yeah, so the best known result is like 1.72 approximation for the unweighted case.
Yeah, thanks. Sorry, in the interest of time, we have to move on, but let's thank Debajyoti again.